Every battery you own is already dying. The battery in your phone is dying. The battery in your drill is dying. The battery in your car is dying. And the expensive lithium pack sitting in someone's garage right now, sold as the future of home energy, is also moving slowly toward the day it will no longer hold a useful charge. You are told this is normal. You are told batteries wear out, devices age, performance drops, and every few years, the only sensible thing to do is buy another one. But more than 100 years ago, Thomas Edison built a battery that challenged that entire idea. A battery that did not rely on lithium. A battery that did not rely on lead acid. A battery that could be fully drained, neglected, refilled, recharged, and brought back to life again. And the strangest part is not that Edison built it. The strangest part is that some of these batteries are still working. Not after 5 years. Not after 10. After generations. And once you understand why this battery disappeared from everyday life, the story stops being about chemistry and starts becoming a question about the kind of world we were sold. Because a battery that lasts for decades is not just a better battery. To the wrong industry, it is a terrible business model. At the start of the 20th century, the future of transportation was not as obvious as people think. Gasoline had not yet won. Electric cars were real, common enough to be taken seriously, and in some cities, they were considered cleaner, quieter, and more reliable than the noisy combustion machines competing beside them. But they had one major weakness. The batteries were terrible. Lead-acid batteries were heavy, corrosive, slow to charge, and short-lived. They could power a vehicle, but not well enough to make electric transport dominate the century that was coming. Thomas Edison saw the problem clearly. He believed the world needed a battery that could survive hard use, deep discharge, vibration, cold, neglect, and time itself. So he started testing. Thousands of combinations, different metals, different electrolytes, different plate designs. Again and again, the early cells failed. But Edison kept going until he arrived at a chemistry that was almost shockingly simple. Nickel, iron, and an alkaline electrolyte. The nickel-iron battery was born. Instead of lead plates sitting in acid, Edison's cell used iron and nickel compounds in a solution of potassium hydroxide. When the battery charged and discharged, the chemical reaction moved back and forth without destroying the plates in the same way lead-acid batteries slowly destroy themselves. That was the key. Most batteries age because their internal structure degrades. Materials break down, crystals form, plates corrode, capacity fades. But the nickel-iron battery was different. It was rugged. It tolerated abuse. It could be drained completely flat and survive. It could sit unused for years and often be revived. It did not burn the way lithium batteries can. It did not spill sulfuric acid like a lead-acid battery. And it could last so long that the word durable almost feels too small. Edison did not see this as a curiosity. He saw it as the storage battery of the future. He imagined electric vehicles, farm equipment, rail systems, mining lamps, signal stations, and backup power systems running on cells built for endurance, cells that ordinary people would not have to replace every few years. And for a while, the battery did exactly that. Railroads used nickel-iron batteries for signal systems because reliability mattered more than weight. Mines used them because the cells were strong and could survive harsh conditions. Remote buildings used them because they could sit in places where maintenance was difficult and still keep working. They were not perfect. They were not lightweight. They did not deliver sudden bursts of power as well as lead-acid batteries. They charged slowly. They produced gas during charging, which meant ventilation mattered. And for vehicles, especially once gasoline engines became dominant, those weaknesses became important. But for stationary power, lighting, off-grid storage, backup systems, and slow, steady energy use, the nickel-iron battery had one quality that modern batteries still struggle to match. It refused to die, and that is where the economics become uncomfortable. A lead-acid battery gives the manufacturer a new sale every few years. A lithium battery creates a replacement cycle too. Phones, laptops, tools, electric bikes, home storage systems, all built around the assumption that the battery will eventually degrade. And when it does, the customer returns to the market. But a nickel-iron battery can last for decades, sometimes far longer. From the perspective of a homeowner, that is incredible. From the perspective of an industry built on replacement, it is a problem. Because permanence does not create recurring revenue. A battery that can be maintained with water and electrolyte does not generate the same service economy as a sealed pack that must be replaced when performance drops. A battery that can survive abuse does not create the same urgency to upgrade. And a battery that lasts longer than the person who bought it does not fit easily into a business model that depends on constant consumption. That does not mean the nickel-iron battery vanished only because of some single secret meeting or one dramatic conspiracy. The truth is more ordinary, and in some ways, more disturbing. It was heavy. It was slow. It was less convenient for the direction the market chose. Gasoline became cheap. Combustion cars became dominant. Lead-acid batteries were better suited for starting engines. Later, lithium batteries became smaller, lighter, and more powerful for portable electronics. The nickel-iron battery did not disappear because it did nothing well. It disappeared because the thing it did best was not the thing modern consumer markets valued most. It lasted. And in a world that increasingly rewarded lightweight, sealed, disposable, upgradable products, lasting too long became almost a disadvantage. But in communities that valued repairability over convenience, the story was different. Among off-grid builders, railroad workers, remote cabin owners, and some Amish communities, old nickel-iron cells remained useful because the priorities were different. The question was not whether the battery was modern. The question was whether it still worked. Could it power lights? Could it survive winter? Could it be maintained without a specialized technician? Could it sit in a barn, a shed, or a workshop and keep doing the job year after year? For those uses, Edison's old battery still made sense. And that is why the image of an old steel cell on a shelf is so powerful. Because it represents a different philosophy of technology. Not faster, not sleeker, not smaller, but repairable, understandable, survivable. A device built for a world where people expected to maintain what they owned, instead of throwing it away when the sealed black box inside stopped working. The chemistry itself is not mysterious. A nickel-iron cell uses nickel-based material on one side, iron on the other, and potassium hydroxide as the electrolyte. During charging and discharging, ions move through the alkaline solution and electrons move through the external circuit, allowing stored energy to be released. The plates can survive cycles that would destroy other battery types. The electrolyte can be replaced. Water can be added. The cell can be brought back from conditions that would make a modern sealed battery worthless. But that repairability comes with responsibility. Potassium hydroxide is caustic. Charging can release hydrogen gas. Improper construction or handling can be dangerous. So this is not something to treat like a casual weekend experiment. The important point is not that everyone should build one in a garage tomorrow. The point is that a battery chemistry existed, was proven, and remained useful for more than a century because it was designed around endurance rather than planned replacement. And that idea raises a larger question. How many technologies were left behind not because they failed, but because they did not create enough future sales? Because the nickel-iron battery is not the only example. Again and again, older systems that were durable, simple, and repairable were replaced by products that were more convenient, more compact, and far more profitable over time. The new systems were not always worse. Many were genuinely powerful and useful, but they also changed the relationship between people and the things they owned. A farmer could understand a mechanical tool. A homeowner could repair a simple system. A workshop could maintain equipment built from visible parts. But sealed batteries, sealed electronics, proprietary chargers, smart modules, and disposable packs moved control away from the owner and toward the manufacturer. And once that happened, replacement became normal. A dead battery no longer meant maintenance. It meant shopping. That is the quiet shift Edison's battery exposes, because a century-old cell that can still accept a charge is almost offensive to the modern economy. It proves that some things can be built to last far longer than we are told to expect. And it reminds us that durability is not a fantasy. It is a choice. A design choice. A business choice. A cultural choice. Today, nickel-iron batteries still exist, mostly in niche applications, off-grid systems, restoration projects, and places where long life matters more than compact size. They are not the best battery for every use. They are not ideal for phones, laptops, or high-performance electric vehicles. But for stationary storage, for backup power, for slow, steady use, they still reveal something modern battery marketing rarely emphasizes. The most advanced solution is not always the one with the highest energy density. Sometimes the most radical solution is the one that does not ask to be replaced. And that is why this story matters. Not because Edison's battery is perfect. It is not. It is heavy. It is bulky. It charges slowly. It needs ventilation. It requires safe handling. But it also does something astonishing. It challenges the assumption that batteries must be temporary. It challenges the idea that decline is unavoidable. And it challenges the entire model of buying the same solution again and again, every few years, forever. So the next time a device dies because the battery no longer holds a charge, remember that more than 100 years ago, Edison built a battery that could survive neglect, abuse, and time itself. A battery that was too heavy for the future we chose, too slow for the markets that won, but perhaps too durable to ever fully disappear. Because somewhere, in an old workshop, a remote cabin, a railway signal box, or a barn shelf, one of those steel cells may still be doing what it was built to do. Holding power, waiting patiently, and proving that not everything has to die on schedule.